So here is another circle graphed in pink. This is the circle of radius 5, centered at the origin. So my formula is now x squared plus y squared equals 25. And at least for this function, I'm jumping the gun, at least for this curve, I could think of it as maybe not one function, but as the graphs of two different functions, which happen to have both been colored in the same pink color. So if I say f of x equals the square root of 25 minus x, well, how did I get that? I just solved this equation here for y, and I took a square root. I would get the top half of that circle, and it's been graphed here in blue. Well, that's only the top half of the circle, and so if I graphed instead g of x equals negative square root of 25 minus x squared, then I would get this lower half of that circle. Looking pretty good, Buttercup. So maybe I could calculate my derivatives that way, just always split up curves, which aren't functions, into different pieces and then do my derivatives that way. And that'll work some of the time, not always. So here's an example of a curve, which again is not a function. So Descartes worked on this. The equation is x cubed minus y cubed, x cubed plus x, gosh, that is tiny. X cubed plus y cubed equals 6xy. There we go. By the way, this is the same Descartes who gave us the Cartesian plane to begin with. Hey, cool, history. So this is definitely not a function because I can see vertical lines where the curve will cross the same vertical line in two or more places. They're not drawn in here. I've put my mouse in a spot where the function fails the vertical line test. Definitely not a function. Can I chop this up into pieces which are functions? Well, this curve I could. So here again, they are in blue and green and yellow. So this blue curve, that's a function. This green curve, that's a function. This yellow curve, that's a function. Well, that's not as handy, right? I don't immediately see a way I can go from the formula x cubed plus y cubed equals 6xy and find formulas for these separate pieces of the graph. That's a hard thing to do, but fortunately, I don't have to. So what we're going to do is we'll say that f of x is a function which is implicitly defined by the equation. So really when I'm saying x cubed plus y cubed equals 6xy, that y is some function of x that I just don't have a formula for. So I could say this is x cubed plus f of x cubed equals 6 times x times f of x. And that implicitly gives me a function. Implicit here just means that I don't actually have a formula for it. But that's not going to keep us down. So how do we find the derivative? How do we find the slopes of those tangent lines for implicit functions? Functions where, well, we've got some part of a curve. Maybe we've chopped it up nice to make it a function, you know, chop it up into a couple different pieces. How do I actually find that tangent line? How do I find that slope? Well, Here is the way we would do it for the circle. X squared plus y squared equals 25. That equation defines a curve in the plane. Let's find the slope of that curve. Let's find dy on dx. And secondarily, find an equation of the tangent line to the circle at coordinates x equals 3, y equals 4. All right. Well, step one, we're going to differentiate both sides of the equation. Ho ho. So here we've used our Leibniz notation again. The differential operator is d on dx. On the left, I have d on dx applied to the quantity x squared plus y squared. Well, since x squared plus y squared equals 25, the derivative of that left-hand stuff should be equal to the derivative of 25. Oh, wait just a minute. 25 is a constant, so its derivative is going to be 0. That tells me that derivative d on dx of x squared plus d on dx of y squared has to be equal to 0. So I can always break up my derivatives across addition. Very nice to do. Let's keep moving. Well, I got to use the chain rule for that derivative of the y squared. So very good of us to learn the chain rule before getting to this section of the textbook. If I want to calculate the derivative, d on dx of y squared, that's going to be, that's going to be the derivative of my outside function, which is the squaring function, times the derivative dy on dx. So I'm just pausing here a bit because they have decided to write the chain rule in Leibniz notation. And though I am partial to that, it's not always the most convenient way to write the chain rule. Here we have 2y dy on dx. Or if you prefer, the derivative of this could be 2y y prime, right? Just a different way to write that idea. So my derivative of x squared is 2x, right? We can do power rule, super duper simple. My derivative of y squared is 2y times dy dx. A little bit more complicated because of the chain rule. This is what happens when you directly apply the differential operator to a formula that's written in a different variable. So again, my d on dx applied to y squared. So I got to differentiate. I'll have my 2 times y, but then I have my dy on dx here because my original derivative operator was in the x variable and I took a derivative in the y variable. This derivative converts between the two of those things. Derivatives convert between rates of change for different variables, because derivatives tell you how much the variable y changes when the variable x changes. I like to say this stuff a lot because it's important, and I hope that it's making sense. Let's continue with this equation, which looks shockingly familiar to the stuff that was on my notebook, just that the division has happened in a different place now. So I have 2x plus twice y dy on dx is equal to 0. Well, I know how to subtract. I know how to divide and cancel. So it must be that dy on dx is equal to negative x on y. Well, cool. Once again, I need both the x coordinate and the y coordinate together in order to know what that slope is. Because there are points of that circle who have the same x coordinate, but different y coordinates. You can think about this as the y coordinate is telling me which of those different pieces we have cut up that we're actually using. So the y coordinate is telling me whether I'm on the top half of that circle or the bottom half of that circle. They will have different slopes. So part 2, let's actually find the slope at coordinates 3, 4. So all I have to do is plug in x equals 3, plug in y equals 4, and I find that my slope is dy on dx equals minus 3/4. Now I can use that to find my tangent line. So one of my favorites for tangent lines is to use point slope formula. So y minus y coordinate equals slope times the quantity x minus x coordinate. Here I've got y minus 4 equals negative 3/4 times quantity x minus 3. And this is the slope of the tangent line. And that is absolutely how I made this diagram in Desmos. So here the t parameter is telling me, well, the coordinate at t should be x equals cosine of t, y equals sine of t, and negative x divided by y in this case will be minus the cotangent. And that is how I graphed this. So if you really wanted to, you could take this tangent line and rearrange, maybe call that 3x plus 4y equals 25. And that's going to be our tangent line. Now, if I tried this the other way, if I broke into 2 different pieces, I certainly could do that with this circle. Let's say y equals plus or minus the square root of 25 minus x squared. Well, if my coordinates is 3, 4, that's a positive y value, so we must be on the upper half. I take the positive square root. So I'll have to use the chain rule to calculate that derivative. F prime of x equals 1/2 times quantity 25 minus x squared raised to the power minus 1/2, all times the derivative of that inside function, d on dx applied to quantity 25 minus x squared. Okay, well, that derivative is going to be minus 2x. So this is what the chain rule tells me the derivative should be equal to. I can simplify that a little bit. My derivative is equal to minus x divided by square root of 25 minus x squared. Alrighty. So at x coordinate 3, f prime at 3 tells me the slope at x coordinate 3. So I just plug in x equals 3 and I get minus 3/4. Just the same. Now, I'm able to do this both ways for the circle because the circle is easy enough to split into a top function and a bottom function. But I don't get to do that every single time with implicit functions this way. So being able to calculate the differential operator gives us a new tool. We can now find slopes for things which are not strictly functions in x, no matter how bad that formula gets.